Welcome to this session on in-database machine learning, Automate, Scale, Deploy. I'm Mark Hornick, Senior Director for Oracle Machine Learning Product Management. Should you be using in-database machine learning? Well, in this session, we'll explore some issues faced by data science teams and how in-database machine learning increases productivity, scales to enterprise needs, and simplifies production deployment. We all know that data volumes are growing exponentially, and data science teams increasingly question if moving data around is a sound architectural choice. Is moving data slowing you down and complicating your solution deployments? Are you looking to bring the computations to the data rather than shuttling data between data stores and analytical engines? In-database machine learning from Oracle can eliminate the need to move data by bringing the algorithms to the data. Do you have the right interfaces? Data science team members often prefer one language over another, for example, Python, SQL, R, or REST. Still others look to use no-code user interfaces and automated machine learning. Allowing each user to work in a common environment on the same data, easily sharing results, supports group productivity. Oracle provides machine learning from such interfaces using the database as a unifying core. How successful are your efforts moving your machine learning projects from the lab to launch, from development to production? Gartner predicts that through 2022, only 20% of Analytics Insight will deliver business outcomes. And VentureBeat notes that 87% of machine learning projects never make it to production. In-database machine learning from Oracle directly supports MLOps goals so you can avoid becoming part of the 87%. For many companies, Oracle Database and Autonomous Database already provide data management, relying on its scalability and performance along with backup, recovery, and security. With machine learning included in the database as part of Oracle's converged database strategy, it's a good time to take a closer look at in-database machine learning. Let's frame this discussion in the context of a standard machine learning process, the Cross-Industry Standard Process for Data Mining, or CRISP-DM. Business understanding has to do with defining the problem to be solved and the success criteria against which the solution will be judged. This is where executives, line of business managers, data scientists, and domain experts need to collaborate before moving to the next phases. But our focus today begins with data understanding, which includes data exploration and visualization. It's key to understand what data you have, where it is, and what it means, and to the extent that it's usable. Data catalog services from Oracle provide metadata management, help data professionals discover data, and support data governance. For data preparation, we need to clean data, combine data from multiple sources, and derive new variables, and do this in a scalable and performant way without requiring data extracts to separate analytical engines. Oracle Database consistently proves in benchmarks and customer use cases the effectiveness of processing data in the database, taking advantage of things like query optimization, parallelism, and other performance features. For modeling, we also want to avoid moving data, and that's why Oracle brings machine learning algorithms to the data, just like it does for query processing and analytics functions. In-database machine learning algorithms have been designed for scalability and performance, taking advantage of multi-node machines and special features of the Exadata platform. The evaluation phase requires the business understanding team to assess how well the machine learning solution meets the business objectives and success criteria. And this can be greatly aided by system-provided model performance metrics, model explainability, and prediction details. And for deployment, users need to be able to quickly and easily include model results in applications and dashboards using interfaces that mesh well with the target environment. In-database machine learning streamlines this process as data and machine learning models reside in the database as first-class objects ready for use. Of course, if you want to score data using REST endpoints, you can deploy models to OML services. We'll talk more about that later. So this brings us to the three key OML aspects that we'll explore in the remainder of this session. OML is automated. It increases productivity for data scientists and enables non-experts within database machine learning. It's scalable. With data in the database, you can handle big data volumes with no data movement for data preparation and exploration, as well as model building and scoring. OML is production-ready deployable. Instead of each project developing similar deployment infrastructure that requires its own rigorous QA process, in-database models can be immediately used in production through robust Oracle-provided interfaces, or easily deployed to OML services. There's also infrastructure to deploy R and Python user-defined functions. Let's dive into this further. We'll start with Automate It. What is a typical modeling process a data scientist may go through? Well, you have multiple algorithms to choose from, and which should be selected. We start with one algorithm, build a model, tune it, and hopefully improve the model quality. Note that each algorithm has its own settings or hyperparameters that need adjusting. And then we compare each new model against previous models, selecting the best. And we repeat this process with the next algorithm. Now, as you can imagine, this trial and error approach is both expensive in terms of time and compute resources. It also requires that you understand how to tune each type of model. So let's summarize the pain points associated with traditional machine learning. These include dealing with a process that is potentially complex and highly iterative. There's a need to understand individual machine learning algorithm hyperparameters and requirements in enough detail to get high-quality models. And due to the wide range of algorithms, the modeling process is often time-intensive to explore the space of candidate algorithms and their corresponding hyperparameters. Solutions to these pain points include introducing an efficient machine learning pipeline that eliminates the brute force approach to exploring the hyperparameter search space. We want to eliminate repetitive modeling tasks through automation, with the goal to increase model quality and user productivity. Let's also apply machine learning to the machine learning process itself to automatically home in on the right algorithm, the right features, as well as the hyperparameters to build high-quality models. We want to make machine learning accessible to a broader audience while reducing the time required to produce the desired results. To realize this, we've introduced Oracle Machine Learning AutoML UI, a no-code user interface supporting automated machine learning. This supports both data scientist productivity and non-expert user access to powerful in-database algorithms. It accelerates machine learning projects by giving quick feedback on dataset suitability for producing useful models, as well as building final models for production deployment. This removes much of the drudgery of the modeling process. Oracle Machine Learning AutoML UI automates model building with minimal user input, as we'll see in the demonstration. For selected models, users can also generate editable starter notebooks written in Python with OML for Py. And deploying models as REST endpoints to OML services takes just a few clicks. Let's have a demonstration of the AutoML UI. Here we're looking at the Oracle Machine Learning user interface. We'll start with the AutoML user interface by clicking the AutoML icon in the Quick Actions. On this screen, we have our listing of AutoML experiments, and the one that we created earlier, Affinity Card 360, which we're going to recreate now. So we'll call this experiment Affinity Card 360 V2. We select the data we want from our database tables. We search here for the schema OML user and choose the table Customers 360. We then select our target column, what we're trying to predict, which is Affinity Card. We can also optionally specify a case ID or unique identifier to enable greater repeatability. Notice that the prediction type is automatically set to classification. This is based on the target data type. AutoML supports both classification and regression problems. Now you'll notice from our table that various statistics are available on our predictors and target columns. And there are additional settings that users can set as well. With our experiment specified, we can start our experiment choosing one of two options: faster results and better accuracy. Faster results uses fewer pipeline combinations. Better accuracy focused on a broader range of pipeline combinations. We'll go with faster results. So we're starting the experiment. We see that it's running, and we get the progress bar defining the workflow we introduced earlier. We start with algorithm selection to decide which algorithms are predicted to give the best accuracy. We then have adaptive sampling and feature selection. And this is followed by model tuning. And finally, feature prediction impact. We're going to let that run, but let's jump over to an experiment that's already completed. Here we see the 5 models that have been produced. A generalized linear model produced the best result. And from here, we could look at model details, prediction impacts, as well as select a model to deploy, rename the model itself for easier recognition, and create a notebook from that. We can also see additional metrics that were computed for each of the models. So the second component we'll talk about that supports AutoML is Oracle Machine Learning for Python. OML for Pi empowers data scientists with Python for in-database machine learning. OML for Pi leverages the database as a high-performance computing environment, allowing users to manipulate database tables and views through data frame proxy objects. You can also use in-database machine learning algorithms through a natural Python interface. Other features we'll touch on later, but let's focus on automated machine learning. Note that AutoML provides the API that also supports the AutoML UI that we just saw. Here's a brief demonstration of OML for Pi AutoML. From the Oracle Machine Learning user interface on Autonomous Database, we'll click on the Notebooks quick action, which takes us to our list of notebooks. We'll open OML for Pi AutoML classification. In this notebook, we start with a markdown paragraph that introduces OML for Pi with the AutoML features we'll cover, namely automated algorithm selection, feature selection, and model tuning. First, we import libraries. In this paragraph, we import Pandas, OML, and the AutoML subcomponent of OML. Running this paragraph establishes the connection from the Python interpreter to the database. Next, we create a proxy object using OML sync for the wine table in the database, which was created from the scikit-learn dataset. And we show the table shape and column data types. In preparation for AutoML, we keep with the Python convention and separate predictors from the target using standard Python syntax. This produces 2 more proxy objects while the data remains in the database. For classification, we'll use the target column called target. We can look at some of the data in our table using the overloaded head function. Here are the first 20 rows retrieved via the proxy object wine. The first AutoML step is automated algorithm selection. While AutoML supports both classification and regression, we'll focus on classification in this demo. Here we define the mining function as classification. The score metric is accuracy, and how much parallelism we should use. Next, we invoke select using our data frame proxy object, and that we'd like the top 4 algorithms returned. In the result, SVM Gaussian was chosen as the best, with 98% accuracy, followed by SVM Linear, Neural Network, and Random Forest. Next is automated feature selection. In this case, we're looking to find which features are most relevant for the algorithm just selected. We create our feature selection object and invoke the reduce function using the algorithm we selected above, which is support vector machine, and provide the data proxy objects, both predictors and target. We see that the number of columns has been reduced from 13 to 9. For automated model tuning, we specify the model tuning object and invoke the tune function, specifying the selected algorithm, the reduced set of predictors, and the target. From this, we see the resulting support vector machine model with the hyperparameters that were used. This completes our quick demonstration of OML for Pi AutoML. Data scientists often want to build models explicitly, even if they use AutoML to get a jump start. For this reason, a variety of automation capabilities have been built into the database algorithms. These include algorithm-specific automatic data preparation, such as the one-hot encoding of categorical variables and binning or normalizing numeric variables. OML supports integrated text mining through an integration with Oracle Text, where one or more columns can be identified as text and features are automatically extracted and combined with other structured data for model building. Partitioned models automate the creation of an ensemble, where a model is built on each partition of data, specified by one or more columns, but used and managed as a single top-level model. Here's an example using OML for SQL, where we build a model to predict if customers are likely to buy travel insurance using PL SQL and the Auto Data Prep feature. We then score an individual customer using the SQL query to see that this customer score is 0.92, indicating being very likely to buy insurance. There are many other ways to build models and score data with SQL. We provide template example notebooks with OML notebooks on Autonomous Database. These examples use the R and Python interfaces, where users build models using familiar R and Python syntax. For R, we use RFormula, and for Python, we use the fit function with separate predictor and target data frame proxy objects. The predict function returns the set of predictions as a proxy object as well, so the results stay in the database. Then the overloaded table or crosstab functions compute a confusion matrix using these proxy objects, so the data again never leaves the database. Next, we'll talk about scalability. Scalability can occur at many levels, whether to access data, explore and prepare that data, build models, deploy solutions, or support concurrent users on the data science team. Focusing on modeling, many factors affect the model building performance and scalability. Data volume is perhaps the most obvious and related to data movement and loading, which can be the real bottleneck if needing to move data from data sources to separate analytical engines and back. This time needs to be considered when comparing machine learning tool architectures. The choice of algorithm. Different algorithms can have vastly different computational demands. Algorithm implementation. Many implementations are single-threaded and simply don't scale. OML in database algorithms have been designed to take advantage of multiprocessor and multi-node hardware, which is essential for improving performance and scalability. The plot here shows near linear scalability for model building with data ranging from 100 million to 800 million rows on Autonomous Database. We also see that the choice of algorithm, even on the same data, has a significant impact on runtimes. Concurrent users also need to be taken into account. One data scientist working on a single model on a dedicated machine will see different performance from multiple users working concurrently in the same environment. As shown here, Autonomous Database's autoscale feature helps meet the needs of multi-user teams. With respect to scoring, this plot shows scoring performance, where again we see essentially linear scalability. The two plots on the left show runtimes from dynamic scores, where the scores are computed off the current data on the fly. The plot on the right shows materializing those scores for later availability as a batch table. In Exadata, scoring takes advantage of optimizations to push scoring operations to the storage tier. On Autonomous Database, autoscaling also supports multiple users working concurrently. Now let's discuss deployable using production-ready infrastructure. When it comes to solution deployment, many data science teams end up reinventing the infrastructure wheel. to work with separate analytical engines. Using tested production-ready tools rather than developing such tools from scratch can be a major benefit. Each one-off solution needs to take into account a wide range of failure conditions, while also ensuring robustness, scalability, and security requirements. This can make a solution more expensive and complex. Such issues help to explain the VentureBeat observation that 87% of machine learning projects fail to go to production, or Gartner's that only 20% of analytics insights deliver business value. For many companies, Oracle Database or Autonomous Database are already a key part of their data infrastructure, delivering a robust, scalable, and secure data management environment. Oracle also provides key infrastructure for deploying machine learning solutions, which includes immediate access to models for insights and for scoring through multiple APIs. When using R or Python environments, application developers already use SQL and REST, but may be less familiar with analytical tools in R and Python. All the same, they need to leverage data scientist R and Python scripts. Oracle provides the infrastructure to do this easily. And OML enables you to score data using REST endpoints for scoring with real-time applications using OML services. So with OML services for Autonomous Database, Oracle makes it even easier for application developers to integrate machine learning models with applications from a REST API. OML services enables key elements of the machine learning lifecycle, supporting an MLOps strategy, including model deployment, update, and versioning. OML services provides fast data scoring for streaming and real-time applications, even faster than in-database scoring. The model management and deployment services enable users to deploy in-database machine learning models, and users can also deploy ONNX format models produced by other Python engines, using packages such as TensorFlow, PyTorch, or others. OML services also supports cognitive text analytics like extracting topics and keywords, sentiment analysis, and text summary and similarity. So let's have a quick demonstration of OML services. In this example, we use the score endpoint to invoke a classification model with prediction details. We specify the input record to score and specify that we want the top 5 features. Then we send the request. In the result, we get back both the 0 and 1 probabilities. In this case, the customer has a predicted score with 0 and a 93% probability. The explanatory details include the predictors and their corresponding weights, identifying how each contributes to the prediction. When it comes to modeling and production-ready deployment, there are multiple ways to produce and consume models using Oracle Machine Learning. Here, with the AutoML UI, models produced in an experiment can be deployed to OML services for use by enterprise applications, including those based on Oracle Apex through REST endpoints. As mentioned earlier, users can also generate a notebook for a selected model and customize the generated Python code, then run the notebook, which builds the model. Users can then export and deploy this in-database model to OML services for use by applications, or use that model directly from SQL or Python. Of course, applications can use models produced by the AutoML UI directly from SQL queries and Python code. Those same models are also available from Oracle Analytics Cloud, leveraging OAC's integration with OML for scoring and visualization. Similar paths are available for models built directly in OML notebooks or third-party IDEs. In this scenario, we use open-source Python or OCI Data Science to build models using a variety of packages and export those models in ONNX format. We can then import these models to OML services. As we noted earlier, deploying solutions using R and Python engines can introduce challenges for application developers. Oracle Machine Learning supports embedded execution to deploy R and Python solutions using database-spawned and controlled engines. OML for R supports an R and SQL interface while OML for Pi supports Python REST and SQL interfaces, depending on the platform. An additional benefit is the ability to easily specify data parallel and task parallel processing. For example, we can store a Python model in the database and use it to score large volume data across multiple Python engines. Each engine scores chunks of data, perhaps 10,000 to 1,000,000 rows at a time. The score results across all engines remain in the database and can be immediately accessed as a database table. OML for Pi and OML for R simplify application implementation with this core infrastructure. To visualize this, consider that data scientists could leverage additional Python packages like scikit-learn and matplotlib to develop and deploy solutions with user-defined functions stored in the database. This serves as a handoff to application developers. Then, using REST endpoints, developers can easily deploy the data scientist's work using database-spawned and managed Python engines, where functions and data are automatically loaded. There are a few other questions to consider involving production-ready deployment. Do you understand your AI results? And how will this impact end-user acceptance of your solution? Why did your model make the prediction it did? Why will this customer churn? Why will this engine part failure? Or why did the loan applicant get denied? It's important to have production-ready built-in capabilities for things such as model explainability, that is, which predictors most impact predictions, as well as model details for the inner workings of the model and evaluation results. And perhaps most important are individual prediction details, which indicate the values that most contributed to a specific prediction. These all help to make your AI solution deployments more successful because it puts more information in the hands of decision makers and application end users. To summarize, here's the broader Oracle Machine Learning product family that supports data science projects. You've seen that OML provides interfaces for SQL, R, and Python. For code-based interfaces with Autonomous Database, we provide OML notebooks with SQL, PL/SQL, Python, and Markdown interpreters, and the same notebooks can contain both SQL and Python paragraphs, allowing users to choose the most effective language for the task. Oracle Data Miner is a SQL developer extension that supports analytical workflows through a drag-and-drop user interface that's compatible with on-premises and DBCS databases. Oracle Machine Learning for Spark provides machine learning from an R interface in the big data environment, such as Big Data Service. And as we saw earlier, Oracle Machine Learning AutoML UI is a no-code user interface that automates model building and deployment. Finally, Oracle Machine Learning Services is a RESTful service for model deployment and management, along with cognitive text analytics. The Oracle Machine Learning tagline is, "Move the algorithms, not the data." As such, Oracle has placed powerful machine learning algorithms in the kernel of the database software. This enables you to automate, scale, and deploy production-ready solutions for your machine learning projects. OML is part of Oracle's converged database strategy, alongside spatial and graph analytics, blockchain, and other technologies. OML delivers over 30 in-database algorithms accessible through a SQL API, and open source languages like Python and R, as well as no-code user interfaces. OML in-database features are included with Oracle Database licenses and cloud-based databases, including Oracle Autonomous Database. To learn more about Oracle Machine Learning, check out the Live Labs, where you can quickly spin up an autonomous database and work through various use cases and scenarios using OML technology. Included with OML notebooks on Autonomous Database are template examples for our SQL and Python interfaces. Examples are also at our Machine Learning GitHub repository. This includes notebooks, but also scripts for use with OML for R. Through our OML office hours, we have a rich library of recorded sessions with product demonstrations, use cases, and application integrations. Sign up to receive notifications of new sessions today. Check out our on-demand sessions, Automating the Machine Learning Modeling Process, and You Have a Model, Now What? If you've missed any of today's sessions, check out the replays. And if you're interested in trying OML for Pi, check out our OML for Pi Live Lab. Python users build intelligent applications faster with Oracle Machine Learning. I also invite you to check out the Oracle Cloud free tier and get a 30-day free trial. Click the link shown here. Thank you for attending this session.